Imagine writing a program, right, where using a single standard true or false variable is considered, uh, well, a catastrophic waste of space.
Yeah, which sounds completely wild to any modern developer.
Right. Because today we are looking at an absolute masterclass in
Yeah,
extreme software optimization. We are so glad you're here with us for this deep dive.
it is going to be a fun one.
It really is. Our mission today is to examine this raw text file containing C code for a motor controller. And the whole system runs on just 64 bytes of memory.
Yep. 64 bytes.
Not gigabytes, not megabytes, not even kilobytes.
Yes.
64 single bytes.
It's just an impossibly tiny amount of space.
It is. And to achieve complex user interface logic within that microscopic footprint, the developer literally hijacked the microchip's emergency self-destruct timer just to figure out if a user double-clicked a physical button.
It is just a stunning piece of engineering. I mean, when you review embedded systems, you often see developers fighting against the hardware limitations.
Oh, totally. Like complaining about the lack of RAM.
Exactly. They complain about the RAM or the slow clock speed, and they try to force these desktop-style programming paradigms onto tiny microcontrollers.
Which never works out well.
No, it doesn't. But the code we are analyzing today, which is titled PowerButton.pwm.txt, it does the exact opposite. It leans right into the architecture.
It embraces the constraints.
Yes, it exploits the physical quirks of the silicon to achieve things that honestly shouldn't mathematically fit into such a constrained environment.
Which is exactly what we're going to decode today, like precisely how this developer pulled this off.
Right.
So, to set the landscape, based on the source comments, our target hardware is the ATINI13 AVR microcontroller. And we have a very specific, limited hardware canvas.
The physical setup is the entirety of our universe for this analysis.
Right, so B1 and B3 are designated as our two input buttons. B2 is an LED indicator, and B0 is our output of PWM, or pulse width modulation signal, driving a physical motor at roughly 30 to 60% capacity.
Exactly. So that's two inputs, one visual output and one mechanical output. And standing between all those physical components is the ATINI13.
It's sort of like, well, programming an ATINI13 is like trying to pack a 5-bedroom house into a tiny studio apartment, right?
That is the perfect analogy.
Every single millimeter, or in this case, every bit of memory and CPU cycle has to serve a specific, highly optimized purpose.
It has to, because treating this chip like a modern CPU is just a fundamental mistake.
So let's establish the reality of this microcampus. If we look at the environment established at the very top of the code, the system clock is defined by the macro FCPU 4800,000UL.
Which means it's running at 4.8 megahertz.
Or 0.8 megahertz. Okay,
It
so
means the processor is executing roughly 4.8 million instructions per second.
right. And if we contrast that with a modern smartphone processor running at like 3 gigahertz.
Oh, yeah. Which executes billions of instructions across multiple cores simultaneously. When you compare them, you begin to really grasp the scarcity we're dealing with.
It's like comparing a bicycle to a bullet train.
Literally. But the clock speed isn't even the tightest bottleneck here. It's the memory architecture.
The 54 bytes.
Exactly. The ATINI13 uses what's called a Harvard architecture.
Okay, unpack that for us.
So a Harvard architecture physically separates the flash memory where the program code lives from the SRAM, which is the static RAM where the working variables are stored.
So they are two separate physical spaces on the chip.
Right. It has 1 kilobyte of flash for the code, and as you mentioned, exactly 64 bytes of SRAM for the working memory.
Okay, I have to push back on the hardware choice right out of the gate here, because we live in an era where you can buy a 32-bit ARM chip for less than 50 cents in high volume.
You definitely can.
And those chips have dozens of kilobytes of RAM, and they run at like 48 megahertz. So why would any engineer intentionally subject themselves to the torment of 64 bytes of RAM?
That's a great question.
Like, is it just legacy stubbornness?
That is the core of the issue, and it's a debate happening constantly in embedded engineering circles right now.
I bet.
While a 32-bit ARM chip is incredibly cheap, it is not always the right tool for an ultra-low-power, battery-operated motor controller.
Because of the power draw.
Exactly. An ARM processor, even in its deepest sleep states, often draws significantly more quiescent current, base-level battery drain than a tiny 8-bit AVR chip like this.
Oh, I see. So it would drain the battery just sitting on a shelf.
Exactly. Furthermore, the ATINI13 is physically minuscule. It often comes in an 8-pin package that requires almost zero external supporting components.
No extra parts.
Right, no external crystal oscillators, no complex voltage regulators.
So in mass manufacturing, say, for a cordless drill or an electric toothbrush, shaving off a few resistors saves real money.
It saves millions of dollars at scale. But even more importantly, the A-Tiny is functionally deterministic.
Meaning you can predict exactly how long an operation will take.
Precisely. On a complex 32-bit chip with memory caches and pipeline prediction, it can be notoriously difficult to guarantee that an interrupt will fire in exactly 3 clock cycles every single time.
Because the chip is trying to outsmart the code.
Yes. But on the Atini 13, you have a direct, unimpeded line of sight to the bare metal. You know exactly what the silicon is doing on every single tick of that 4.8 megahertz clock.
Wow. Which brings us to the first few lines of actual code.
Yes.
The include statements. We see standard AVR libraries here.
Right, like intypes.h and avrio.h.
Yeah, and avinterrupt.h. Now, to a standard application developer, an include usually means bringing in a massive library of pre-written functions.
Like bringing in a whole framework.
Exactly.
Yeah.
But in this bare metal context, these aren't really functional libraries, are they?
They are not. I mean, there is no operating system here to abstract the hardware away.
Right.
These header files are essentially topographical maps of the physical silicon. So, for example, avrio.h contains the memory addresses for the internal hardware registers.
So when the programmer types PORTB in the code,
They aren't calling a software variable. They are addressing a specific latch circuit etched into the chip that controls the voltage on physical metal pins.
wow. So this code interacts directly with the transistors.
Directly, yes.
That transition from abstract software to physical voltage is really where this code gets incredibly clever. Let's look at how the developer manages complex states within that unforgiving 64-byte limit.
The memory efficiency here is just beautiful.
It really is. In a standard desktop application, if I need to track whether a system is powered on, I just declare a Boolean, right?
Right, a simple true or false.
And the compiler allocates a full 8-bit byte, sometimes even a 32-bit integer, just to keep the memory aligned on the data bus, merely to store a 1 or a 0.
Which means the remaining 31 bits are essentially dead space.
Dead space. But that kind of compiler padding is a luxury of abundance, isn't it?
It absolutely is. If our developer used standard 8-bit booleans for the dozen or so state flags required by this motor controller, they would immediately consume a massive percentage of their available 64 bytes.
Just on true or false flags.
Exactly. But instead, they utilize a deeply specialized C data structure, the bit field.
Ah, yes. Inside a struct, wrapped inside a union. I am looking at the union for the power variable right now.
Walk us through it.
Okay, inside, it defines the struct with these specific lines. It says volatile AT mode :1, then down :1, up :1, alarm :1.
And button event :1.
Right, and finally, volatile ATT 30X:3. What is going on with that colon syntax?
The colon syntax there is the bit field declaration. The programmer is forcefully overriding the compiler's natural instinct to assign a full byte to each variable.
So they are micromanaging the compiler.
Completely. They are instructing it carve up a single 8-bit byte into individual 1-bit flots.
Wow, so the first 5 flags mode, down, up, alarm, and bud event, they consume exactly 5 bits.
Exactly. And that final line you read, the third X:3.
Yeah, what is that?
That is intentional padding. It fills out the remaining 3 bits, ensuring the entire structure perfectly aligns to exactly 1 8-bit byte in the SRAM.
That is wild. They manually pack the suitcase so nothing rattles around?
That's a great way to put it. And the button structure, the variable name but, takes this even further.
Right, because it tracks several 1-bit flags, like event, pressed, ended, and released CD for the cooldown state.
But then it declares volatile RNA on 8T counter:4 and BR:4.
4-bit nibble.
Yes. A single bit can only represent 0 or 1, but 4 bits in binary can represent values from 0 up to 15.
Because they need to count button clicks.
Right. The developer needs to count how many times a user clicked a button to determine if it was a single click, a double click, or whatever.
And instead of using a full 8-bit integer, which can count to 255,
Which is total overkill for counting button clicks.
nobody double clicks 200 times.
Exactly. So they constrain the counter to 4 bits. They fit a live counter and a secondary memory registered the BR into a single byte.
It is an exercise in absolute spatial efficiency, but I want to focus on that word volatile because it appears before every single one of these bit field declarations.
It's a very important key word here.
Right. In modern software, we want the compiler to aggressively optimize our code. We pass flags like NASH03 to tell the compiler to strip out redundant reads, right?
Right. Keep variables cached in the high-speed CPU registers rather than constantly fetching them from RAM.
So why is the developer deliberately sabotaging the compiler's optimization here by using volatile?
Because the compiler is entirely blind to the physical world outside the chip.
What do you mean by blind?
Well, an optimizing compiler builds a dependency graph of the code. If it sees a while loop checking a variable named button pressed, and it doesn't see any code inside that loop changing the variable, it assumes the variable can never change.
So it just reads the cached value over and over.
Exactly, it optimizes the checkaway.
Hmm.
But in an embedded system, the hardware environment is asynchronous.
Oh, because a human being might physically press the switch.
Yes, causing a hardware interrupt that suddenly changes the value of button pressed in this RAM without the main logic loop ever predicting it.
I see. So the compiler thinks it's looking at a static room, completely unaware that a physical interrupt is sneaking through the window and rearranging the furniture.
That's a fantastic analogy. The volatile keyword acts as a strict barrier against optimization.
It forces the compiler's hand.
It forces the compiler to generate machine code that physically fetches the variable from this RAM address on every single execution.
Regardless of how redundant it seems.
Exactly. It is defensive programming against your own toolchain.
And the crowning achievement of this whole data structure is the union itself. Because the struct containing all those meticulously packed individual bits shares the exact same memory address with a single 8-bit variable declared as volatile EK8 all.
This is a classic, highly effective trick in low-level C.
How does it work in practice?
Well, if you want to reset a complex state machine, you normally have to clear each flag individually. Set mode to 0, set alarm to 0.
Which takes a lot of instructions.
In assembly language, that requires loading the byte into the arithmetic logic unit, applying a bitwise ND mask, and storing it back into SRAM for every single flag.
It wastes program memory and precious clock cycles.
But because power all physically overlays the entire struct, the programmer can just execute power, all equals 0.
Boom. In a single clock cycle, a raw 0 is written to the entire memory address.
Instantaneously clearing every single bit flag within the structure simultaneously.
It's like having a switchboard with 8 individual light switches. Instead of walking down the line and turning off each switch one by one, the union acts as a master breaker switch that shuts them all off in a single pull.
Exactly. It provides granular access when you need to check a single bit and bulk access when you need to reset the system, all without using a single byte of extra memory.
That is so smart. Okay, so we've established how fiercely the code protects its limited memory. Let's look at how it protects the battery.
This is where the power management strategy gets really interesting.
Right. Because when you open up the main function of this program, int main void, the setup sequence configures the hardware, and then you hit the main operational loop.
The while loop?
Yeah. It reads while one, and then just open and close brackets. It is completely empty.
There are literally no instructions inside the loop.
To a software engineer accustomed to writing desktop applications, an empty infinite loop looks like a fatal bug.
It looks like the program will simply hang, burning 100% of the CPU cycles, spinning in place and locking up the system.
Right. But in this architecture, the empty loop is actually the foundation of its power management strategy.
Yes, because this system relies entirely on an event-driven, interrupt-based architecture.
Let's contrast this with the alternative, which is polling.
Right, polling is the standard way a lot of beginners write code.
Like if I'm writing a simple script to monitor a keyboard, I might write a loop that constantly checks. Is the key pressed? How about now? Now? Now?
Exactly. And polling keeps the primary oscillator running and the arithmetic logic unit active.
Which drains power.
In a battery powered at Tiny 13, running at full speed in a polling loop draws roughly 1 to 2 milliamps of current.
That doesn't sound like much.
It might not sound like much, but if the device is sitting idle in a toolbox for 6 months, that constant drain will absolutely flatline the battery.
Which completely explains the macros defined at the top of the file. SMASK, IDLE, power down. These directly interface with the MCU control register to configure the sleep modes.
Yes, they do. When the CPU hits that empty while one loop, an interrupt routine has already executed a sleep command, specifically targeting the power down state.
And what does power down actually do?
In power down mode, the ATINI13 goes into deep hibernation. the main clock oscillator physically stops oscillating.
FRP stops.
The logic gates freeze. The current consumption plummets from milliamps down to roughly 0.1 microamps.
Wow. So it's virtually zero drain.
It's essentially indistinguishable from being unplugged.
Okay, but let me push back on this event-driven architecture for a second. If you are putting the main clock to sleep entirely, aren't you introducing massive latency?
Latency is always a concern.
Right. If this chip is controlling a motorized hand tool, when a user squeezes the trigger, they expect instantaneous torque.
Naturally.
Doesn't the time it takes for the physical crystal or internal oscillator to spin back up from a dead stop create a noticeable, frustrating lag for the user?
That is a highly relevant concern in embedded design. Startup time from deep sleep is a known factor that engineers have to calculate.
So how do they get around it here?
The 18E13 uses an internal 9.6 MHz RC oscillator, which is scaled down by a fuse bit to our 4.8 MHz operating speed.
Okay.
Unlike a physical quartz crystal, which can take tens of milliseconds to physically resonate and stabilize.
Because it's a physical piece of quartz vibrating.
Right. But an internal RC oscillator powers up incredibly quickly, typically within a few microseconds.
Oh, microseconds.
Yes. The latency introduced by waking up from power down mode is entirely imperceptible to human reflexes.
So the user feels instantaneous response.
Exactly, but the battery experiences months of extended shelf life.
That completely addresses the wake-up lag. But what about when the system is actually running?
What do you mean?
Well, if I press the button, the motor starts spinning. But if the CPU goes back to sleep to save power, doesn't the motor just immediately stop? If the brain halts, how does the output continue?
This requires a paradigm shift in how we view microprocessors. The 18E13 is not just a monolithic processing block.
It's not just a calculator.
No, it is a system on a chip. The CPU core, the part executing the C code and doing the math, is just one tenant in the building.
Interesting way to phrase it.
Alongside it, etched into the exact same silicon, are independent hardware peripherals, and in this case, Timer 0.
Timer 0, which is the PWM generator.
Exactly. Timer 0 is a dedicated piece of hardware. During the initialization phase, the CPU configures Timer 0.
It gives the instructions.
It sets the frequency, the duty cycle, and links it to the physical output pin B0. Once configured, the CPU issues the command to start the timer, and then the CPU executes the sleep instruction.
So the CPU core shuts down completely, but the timer peripheral remains powered and active.
Yes. The hardware timer takes over the heavy lifting autonomously.
Wow.
It continuously toggles the physical pin to drive the motor without needing any intervention from the software.
So the CPU can be completely comatose, drawing minimal power, while the hardware peripheral smoothly drives a heavy electrical load in the background.
It is asynchronous hardware delegation at its absolute finest.
That naturally leads to what is arguably the most complex and fascinating mechanism in the entire file.
Watchdog hack.
Yes, because if the CPU is dead asleep and the main loop is empty, how does it handle dynamic, complex user inputs?
Like a double click.
Right. If the motor is running and I double-click the button to change the speed, how does the sleeping CPU know?
Well, the developer solution here is what I would describe as beautifully unhinged.
Perfectly unhinged. They hijack the watchdog timer.
It is definitely the most unorthodox engineering decision in the codebase.
To understand why it's so clever, we have to establish what a watchdog timer, or WDT, is actually designed to do.
At its core, a watchdog is an emergency failsafe.
Like an alarm system.
Right. In critical embedded systems, say, an anti-lock braking system in a car or satellite modules in orbit, you simply cannot afford for the software to freeze.
Because there's no one there to unplug it and plug it back in.
Exactly. If a cosmic ray flips a bit in RAM and sends the program counter into an infinite loop, there is no human operator to press a physical reset button.
Right.
So chip designers include a completely independent hardware timer that runs on its own dedicated 128 kilohertz oscillator.
A completely separate heartbeat, immune to whatever the main CPU is doing.
Yes, and the software's responsibility is to periodically reset this timer, a process colloquially known as petting the dog.
Petting the dog, I love that.
If the software hangs, the petting stops. The independent timer eventually counts down to 0, and the hardware forcefully triggers a systemic reset, rebooting the entire microcontroller from scratch.
It is the nuclear option for fault tolerance.
Exactly.
But our developer isn't using it as a failsafe at all. They are actively suppressing the reset function and reconfiguring the watchdog to trigger a standard software interrupt instead.
Which is brilliant.
In the Watchdog Reset Pro function, they're using it as an ultra-low power, highly configurable egg timer to handle the multi-click logic of the user interface.
The audacity of using a system reset mechanism for user interface debouncing is just, it's brilliant.
It really is.
Primarily because it leverages hardware that is otherwise sitting completely idle, freeing up the primary timer 0 to focus solely on the motor control.
But modifying the watchdog is inherently dangerous, isn't it? The hardware is designed to prevent accidental modification.
Very dangerous, and you can see how they navigate that in the code.
Yes, the very first line inside Watchdog Reset Pro isn't standard C code. It reads, ASM open parenthesis, quote, WDDAR error, quote, close parenthesis.
That is inline assembly language.
They bypass C entirely.
The developer is bypassing the C compiler and injecting a raw mnemonic directly into the instruction pipeline. WDR stands for Watchdog Reset.
So they pet the dog right before changing its collar.
Exactly. Before you can change the watchdog's configuration, you must reset it to prevent it from firing mid-change.
But why inline assembly? Why not just use a standard C function to write to the register?
Because of the strict hardware timing requirements. To change the watchdog settings on an ATtiny13, you have to write a logic 1 to the watchdog change enable bit and the watchdog enable bit simultaneously.
Okay.
Once you do that, the hardware gives you exactly 4 clock cycles to write your new configuration.
4 cycles. That is a microscopic window.
If you take 5 clock cycles, the hardware locks you out and ignores the change.
And a C compiler might insert extra instructions behind the scenes.
It absolutely might. It might push registers to the stack or do some hidden pointer arithmetic, blowing past that 4-cycle window.
So by using inline assembly and carefully structuring the subsequent register writes, the developer guarantees cycle-accurate execution.
Perfectly satisfying the hardware security sequence.
That is incredible. And once they bypass the security, they dynamically shift the prescaler of the watchdog on the fly.
They change the timer duration.
Right. The code defines an enum with values mapping from 16 milliseconds all the way up to 2 seconds. When the initial button press wakes up the sleeping chip via a pin change interrupt, the code immediately calls Watchdog Reset Pro with a 0.
Which sets the watchdog to bark in exactly 16 milliseconds.
And then the CPU goes right back to sleep.
And this specific duration, 16 milliseconds, brings us to the critical concept of software debouncing.
Software debouncing. Let's dig into that. And the physical realities of electromechanical components.
Because this is where abstract logic collides with physical physics.
When I press a button on a drill or a flashlight, I feel a single, clean click. My brain registers one discrete event.
Right, you think it's just on or off. But the microscopic reality is vastly different.
How so?
A tactile switch consists of metal contacts. When you press the button, you are forcing 2 pieces of metal together. But metal is elastic.
It bends.
It has a physical spring coefficient. When the contacts meet, they don't instantly fuse. They smash into each other and microscopically bounce apart, then smash together again.
Like dropping a bowling ball on a trampoline.
Exactly. And as the gap between them narrows to nanometers, you also get electrical arcsing.
The voltage literally jumps the gap.
Yes. Microarcsing and physical rebounding occur simultaneously. So to the microcontroller, which is sampling the pin voltage millions of times a second.
That single human press looks like a chaotic storm of high and low voltage spikes.
If you wire a button directly to an interrupt without debouncing, the CPU will think you pressed the button 50 times in 2 milliseconds.
In standard electronics, engineers solve this with hardware, don't they?
Usually, yes. They place a capacitor across the switch.
So the capacitor absorbs those rapid voltage spikes, acting like an electrical shock absorber, smoothing the chaotic signal into a clean, gradual voltage curve.
But hardware capacitors cost money.
And take up physical space on the circuit board.
In our philosophy of extreme optimization, the developer eliminates the capacitor entirely and solves the physical physics problem purely with time.
Purely with time. So when the initial chaotic voltage drop triggers the hardware interrupt, the CPU wakes up, acknowledges the strike,
Sets the watchdog for 16 milliseconds.
and goes back to sleep. It effectively plugs its ears and ignores the bouncing.
Exactly. 16 milliseconds is mathematically chosen because it is longer than the physical settling time of the mechanical switch contacts.
So when the watchdog wakes the CPU up 16 milliseconds later, the bouncing is over.
The physical bouncing has ceased. The connection is solid.
The code then checks the actual pin state inside the watchdog interrupt service routine using the statement PINB ampersand open parenthesis 1 left shift 3 close parenthesis.
That's a bitwise operation.
Let's break down that bitwise operation for anyone unfamiliar with low-level masking. PINB is the physical hardware register that reflects the live voltage of all 8 pins on port B simultaneously.
It is a raw 8-bit number representing a chaotic jumble of inputs and outputs.
So the developer uses a bitwise A&D mask. The one shifted left 3-foot takes a binary 1 and shifts it 3 slots to the left,
Aligning it perfectly with pin 3.
where our button is connected. And the bitwise A&D operation filters out all the noise from all the other pins, isolating the exact voltage state of that specific button in that exact microsecond.
If the isolated bit is low, the software confirms it as a true intentional human press, setting our bit-packed but.pressed flag to 1.
But this is just the beginning of the state machine, isn't it?
Oh, yeah.
The code is tracking not just presses, but complex intent. The macros BRE1, BRE2, BREB1, and BREB2 indicate a whole matrix of single clicks and double clicks for 2 separate buttons.
It's advanced UI on bare metal.
Walk us through how this hijacked watchdog timer manages to decode a double click without keeping the CPU awake to monitor the timing.
It's an elegant sequence of shifting timescales. After the initial press is confirmed, the user eventually releases the button.
Naturally.
The watchdog wakes up again, reads the pin, and sees the voltage is high. The physical release is confirmed.
At this moment, the code increments our 4-bit variable, but.counter. So the counter is now at 1.
Next, it flags but.release CD equals 1. The CD stands for cooldown, and crucially, it calls Watchdog Reset Pro with a 4.
Which changes the watchdog prescaler from the fast 16 millisecond debouncing rhythm to a long 250 millisecond window.
It sets an egg timer for a quarter of a second and goes straight back to sleep.
It gives the human user exactly 250 milliseconds to make a decision.
Yes. If the user clicks the button a second time before that timer expires, the initial hardware interrupt fires again, the 16 millisecond debounce cycle runs, and the counter increments a second time.
So but.counter becomes 2.
But what if the user doesn't click again?
Right, what if it was just a single press?
Then the CPU remains asleep until the 250 millisecond watchdog timer naturally expires.
A quarter second is up.
The watchdog interrupt fires, wakes the CPU, and the logic evaluates the state. It sees the cooldown flag is active, but no new presses have occurred.
So the state machine finalizes the sequence.
It takes the current counter value and locks it into the final button register with the command but.br equals but.counter.
And if the counter was 2, but.br now holds the value for BRA2, the double-click event, and the main logic can now alter the motor speed based on that event.
The sophistication here is staggering. Achieving this double-click recognition, a featured desktop operating system dedicate entire background services and megabytes of RAM to handle, is accomplished here using a few bytes of bit-shifted RAM.
And a hijacked hardware failsafe.
And an architecture that spends 99% of its time completely asleep.
Unbelievable. So we've established how the chip wakes up, securely reads the physical buttons, calculates complex state matrices like double clicks, and goes back to sleep without burning battery power.
Right.
But that leaves the biggest unanswered question.
Yeah.
If the brain is asleep, what is actually pushing the physical electricity to the motor to make it spin?
Which brings us to the engine room of the code, the phase-correct PWM configuration.
We noted earlier that timer 0 operates independently of the CPU core, but how it operates is dictated by 2 very specific lines in the initialization routine.
TCCR0A equals 1 left shift WGM00.
And TCCR0B equals 5. Let's translate those registers. TCCR0A and TCCR0B stand for Timer Counter Control Registers A and B.
By flipping those specific bits, the developer routes the internal logic gates of the timer hardware into a mode called phase-correct PWM.
To understand why this matters, we have to understand how pulse width modulation actually drives a motor.
Right, because an A10E13 cannot output analog voltages.
It cannot output 2.5 volts to run a 5-volt motor at half speed.
It only has binary outputs, 5 volts or 0 volts, fully on or fully off.
So to achieve variable speed, it rapidly flicks the switch on and off, and the physical inertia of the motor averages out those digital pulses into a smooth mechanical rotation.
Exactly. The ratio of on-time versus off-time is the duty cycle. But the shape of those pulses has profound physical implications for the motor.
Which is where phase correct comes in. Because most basic microcontrollers default to what is known as fast PWM, don't they?
They do. Fast PWM is the standard.
How does fast PWM generate the pulse?
In fast PWM, the internal hardware counter counts up from 0 to 255. Somewhere in the middle, say at 127 for a 50% duty cycle, it flips the output pin high.
Uh,
When the counter hits the maximum value of 255, it instantaneously resets back to 0 and drops the pin low.
If you graph that, it looks like a sawtooth wave. It ramps up and then drops off a sheer cliff.
The problem with a sawtooth wave in a motor control application relates to electromagnetism.
Because a motor is essentially a series of inductor coils.
Exactly. Inductors violently resist sudden changes in current, what engineers call the DEET, the derivative of current with respect to time.
So when fast PWM drops off that sheer cliff back to 0.
It forces a massive instantaneous change in the magnetic field of the coils.
And how does that manifest physically for the user?
It manifests as acoustic noise and mechanical vibration.
Oh, like that high-pitched squeal.
Yes. That whine you often hear from cheap power tools or low-end electronics is coil whine caused by the harsh asymmetric switching of fast PWM.
Which totally explains the developer's choice of phase-correct PWM instead. There's a comment right above those register configurations that maps out the math. Timers Severo phase-correct PWM mode for 800,000 divided by 510 divided by 128 equals 73.
Let's unpack the numbers here, starting with why phase-correct PWM uses the number 510.
Yeah, where does 510 come from?
Phase-correct PWM changes the counting mechanism. Instead of counting 0 to 255 and dropping instantly back to 0, it acts like a pendulum.
A pendulum.
It counts up from 0 to 255 and then smoothly reverses direction, counting back down from 255 to 0.
So 255 up plus 255 down equals 510 total ticks per full cycle.
Yes, because it ramps up and ramps down symmetrically, the resulting pulse aligns to the center of the cycle.
So when you graph it, it looks like a smooth triangle wave rather than a jagged sawtooth.
Like a pendulum slowing down at the apex before reversing rather than hitting a wall and teleporting back to the start.
That symmetry softens the electromagnetic jolt to the inductor coils, doesn't it?
Immensely. The change in current over time is managed more gracefully, drastically reducing the physical vibration and virtually eliminating the audible coil whine.
So the motor runs smoother, quieter, and potentially with better torque transfer.
It's just a vastly superior way to drive an inductive load.
Let's finish the math in that comment.
Yep.
The first number, 4,800,000, is our system clock. The middle number is the 510 ticks of the pendulum. And the final number is 128.
Which comes from setting TCCR 0B to 5.
Right. What does that 5 do?
That 5 fight activates a specific hardware prescaler within the timer circuitry.
Because the 4.8 megahertz clock is ticking far too fast to drive a mechanical motor directly, right?
Exactly. The pulses would be so short the inductive coils wouldn't have time to build a magnetic field.
So the prescaler acts like a mechanical gearbox.
It divides the main clock. The timer only ticks once for every 128 ticks of the CPU clock.
So the final equation is the 4.8 million raw ticks divided by the 510 ticks required for one phase correct pendulum swing divided by the 128 ratio gearbox, which yields an output frequency of approximately 73 hertz.
The switch is flicked 73 times a second, symmetrically, while the CPU sleeps.
It is a masterstroke of configuring the hardware to handle complex physics autonomously.
The developer isn't writing software to spin a motor. They are writing software to construct an independent hardware engine that spins the motor and then stepping completely out of the way.
So if I'm tracking the entirety of this deep dive, we started with a chip that has only 64 bytes of memory and runs at a fraction of the speed of modern processors.
And we found a developer who, instead of fighting those limitations, used them to build a perfectly optimized system.
They bypass the compiler's padding by meticulously carving up single bytes with bit fields and overlaying them with unions for single-cycle resets.
They protected the battery by halting the CPU oscillator entirely.
They solved the physical physics of bouncing metal contacts by hijacking a nuclear self-destruct timer and dynamically shifting its cadence to decode double clicks.
And finally, they routed the raw logic gates of an independent hardware peripheral into a geometric pendulum configuration to silently drive an inductive motor.
It fundamentally redefines what it means to write smart code.
I completely agree.
Today, we often conflate smart coding with abstract complexity using massive machine learning libraries, importing gigabytes of dependencies, or relying on cloud infrastructure.
But true engineering elegance is often found in subtraction. It is found in profound, intimate familiarity with the lowest levels of the physical hardware.
It's the difference between buying a prefabricated mansion and building a perfectly interlocking, frictionless puzzle box.
That's beautifully said. And I want to leave our listeners with a final thought to reflect on.
Go for it.
We exist in a paradigm of unbelievable technological abundance. We write mobile applications that consume hundreds of megabytes of RAM just to render a simple user interface because memory is cheap and processors are blindingly fast.
We rely on that brute force processing power to pave over inefficient software.
We use the massive engine of the smartphone to compensate for the bloat.
We really do.
Precisely. But consider the Attain E13 running this motor control code. Next time you interact with a seemingly simple electronic device, a motorized toothbrush, a power tool, or a smart switch, think about the invisible microscopic ballet of timers, bit shifts, and watchdogs happening thousands of times a second underneath your finger.
It makes you appreciate the unseen engineering.
It does. And if we applied even a fraction of this developer's ruthless, beautiful efficiency, this profound respect for the silicon to our modern computing landscape, how much faster, cooler, and more energy efficient could our massive systems be?
What could we achieve if we stopped treating processing power as an infinite resource to be wasted and started treating it like a microcanvas to be optimized?
That is the real question.
That is a staggering implication for the future of software engineering and a perfect place to wrap up. Thank you so much for joining us on this exploration of the microscopic mechanics inside PowerButton PWM.txt. We will catch you on the next deep dive.